In this question, I will teach you how to find spot interest rates from given bond prices. In this question, we're given three bonds: Bond A, Bond B, and Bond C. Bond A has 0% coupon and has 1 year until it matures. Bond B has a 3% coupon rate and has 2 years until it matures. And Bond C has 3.5% coupon rate and has 3 years until maturity. Bond prices are given as such. So Bond A costs $97.50 right now, Bond B costs $96, and Bond C costs $98. So the goal is to take this information about the bonds in green here and find spot interest rates for years 1, 2, and 3. So this is the question. The first step that we will do here is that we will write the prices of these bonds as the function of interest rates. So let's start with Bond A. So the price of Bond A, PA, would equal to 100% $1 face value that this bond pays at the end of year 1, divided by 1 plus interest rate R1. So this is the 1-year spot interest rate. One thing to note here is that all of the bonds have $100 face value, and all of these bonds are risk-free. So we are talking about spot interest rates, risk-free spot interest rates. So this is for Bond A. The next step is to write the price as the function of the coupon and interest rates for Bond B. So Bond B has 2 years until maturity and pays 3% coupon. This means that if we are the holder of this bond, we will get $3 at the end of year 1, which is our first coupon. We'll get $3 at the end of year 2, which is our second coupon, and then we will get the face value of $100 paid to us at the end of year 2. So now what we do is we're discounting these coupon payments and the face value to present using the appropriate discount rates. So the first $3 we get at the end of year 1, so therefore we're discounting it by discount rate R1. And the second payment, the last coupon and the face value, we're getting at the end of year 2, and therefore we're discounting it to present by using R2 as the discount rate. Hence power 2 here, because this payment comes at the end of year 2. The final step is to do the same thing for Bond C. So the price of Bond C, this bond has 3 years until maturity. It pays coupon 3.5%. So $3.5 discounted by 1 plus R1. So this is our first payment. Our second payment is the next coupon, $3.50, discounted to present at discount rate R2, raised to the power 2 because this payment occurs in year 2. And finally, we get our last coupon at the end of year 3. We get face value of this bond as well at the end of year 3, and we're discounting it to present using R3 as the discount rate. And we're raising it to power 3 because this payment occurs at the end of year 3. Now, the goal is to find spot interest rates R1, R2, and R3. I've written down the prices of these bonds right here, so they're given to us. So what we effectively have here is that we have a system of 3 equations with 3 unknowns. And notice that this is an easy system to solve in the sense that the first equation has only one unknown, R1. So we can solve this equation, plug this R1 into the second equation, at which point this ratio will become known, and this will just become an equation with one unknown, R2, at which point we can solve this equation for R2, plug our known R1 and R2 into the last equation, and solve this last equation for R3. And so this is exactly what I'm going to do now. So I'm going to start solving the first equation for R1. So R1 is going to be equal to $100 divided by 97.50 minus 1. So this would give me the first spot interest rate, R1. So I solve this first equation for the first spot interest rate, R1, and the answer is R1 equals to 2.56%. Now, the next step is to take this known R1 and put it into the second equation. I've erased the third equation here right now so that I have more space to work here. So what I will do here is that I will plug this into this equation. And I will get the following. So I'll get 96 equals to $3 divided by 1 plus 2.56% plus 103 divided by 1 plus R2 raised to the power 2. This is a known number that we can compute. And so this just becomes an equation with one unknown, which I can solve for R2. I just solved this equation for R2, so R2 equals to 5.2%. Now, the last step is to find R3. So I've written down back the bond pricing equation that we had before for bond C. And so right now what I will do is that I will take again R1 that we computed before, and I will put it down here. And now I'll also do the new R2 that we found, and I'll put it into this last equation as well. At which point, again, this will become just one equation with one unknown. So let's do it. So $98 equals to 3.5, 1 plus 2.56%, plus another 3.5, that's our second coupon, divided by 1 plus 5.2% squared, plus 103.5 divided by 1 plus R3 raised to the power 3. So this we can compute, and again, this just becomes one equation with one unknown. So the goal right now is to solve this equation for R3. So I just solved this equation for R3, and I found that R3 equals to 4.22%. And that's how we find spot interest rates. So R1 equals to 2.56%, R2 equals to 5.2%, and R3 equals to 4.22%. This is the answer to this question. So this is how we find, from given bond prices, this is how we find spot interest rates. We always start with finding the closest or the shortest interest rate from the first given bond, and then we continue working and finding the second and the third interest rate. So if we're given fourth bond and we were given 4 periods, we would continue doing that and just solving this equation and stripping this spot interest rates. Now, the last step what I will show you is that I want to actually use this discount rate and make sure that I solve this question correctly, in the sense that if I were to price these bonds using this term structure of spot interest rates, that I would actually get the prices that were given. And I will show this to you right now. All right, so let's compute the prices given the interest rate that we just found. So the price of bond A would equal to, again, it's a zero coupon bond, 1 year to maturity. So it's $100 divided by 1 plus R1. So R1 right now equals to 2.56%. So if we compute this price of this bond A, what we will find is that it equals to $97.50. The price of bond B would equal to the first coupon, so $3 divided by 1 plus R1, which is 2.56%, plus the last coupon, plus the face value divided by R2, which is 5.2%, raised to the power 2, because this cash flow occurs at the end of year 2. So if we compute this price right now with this interest rate, so what we will find is that the price of this bond is indeed $96, the number that was given to us in this question. Finally, the bond price C equals to the first coupon payment, $3.5, because this bond, again, has 3.5% coupon rate, divided by 1 plus 2.56%. This is our R1. Second coupon, $3.50 divided by 1 plus the second discount rate, R2, $5.20, plus the last coupon payment, 3.5, plus the face value received at the end of year 3, discounted by 1 plus R3. That's 4.22%, raised to the power 3, again, because this cash flow occurs at the end of year 3. So if we compute this price, we will find that it also equals to $98. So what we've done, we've confirmed that the discount rates that we found from given bond prices, if we plug them back in and try to price these bonds with these discount rates, that we will indeed find the numbers or the bond prices that were given in this question, which means that we have solved this question correctly. In this question, we will learn how to identify arbitrage opportunities in the bond market and how to take advantage of such opportunities. Suppose that you're a bond trader and you see the following bonds and their prices on your screen. So there are three bonds, A, B, and C. All three have face value of $100. They have corresponding maturities of 1, 2, and 3 years, following coupon rates and prices. Now, there is another bond, Bond D, that just became available in the market. It has the same face value of $100 as bonds A, B, and C. It has 3 years to maturity and a 3% coupon rate. Its current price is $99.50. The first question asks us if there is an arbitrage opportunity in this market, and if yes, asks us to explain how we would take advantage of such opportunity. The first step that we will do in this question is that we will find the term structure of interest rates based on the prices of bonds that are given to us. So in particular, we would use prices of bonds A, B, and C to find interest rates R1, R2, and R3. So these are the spot interest rates for year 1, year 2, and year 3. We would, generally speaking, follow exactly the same approach as we've learned in the first question that we've covered. So let's start with bond A. The price of bond A is given to us as $96.90. So the current price of this bond, because this is a zero coupon bond, it pays $100, which is its face value at the end of year 1. So therefore, the current price should equal to the face value discounted to present at the 1-year spot interest rate. So we have this first equation. What we do is that we solve this equation for R1, which gives us 1-year spot interest rate, R1. In this case, it equals to 3.2%. Now we turn our attention to bond B. We can write down the following pricing equation for bond B. The price of bond B, which is given to us as $99, it should equal to the first coupon discounted to present, plus the second coupon, plus the face value discounted to present. Remember, this is a 2-year maturity bond. It pays 2.75% coupon rate. So therefore, the dollar value of the annual coupon that this bond pays is $2.75. So we take the first coupon and we're discounting it to present at 1-year spot rate, R1. And we take the second coupon and the face value, which we get at the end of year 2, and we discount it to present at R2, which is a 2-year spot rate. So the goal is to solve this equation for R2. Glancing at this equation, it looks like we have R1 and R2 in this equation, but the good news is that we already know R1, which we found from the price of bond A, which was 3.2%. So therefore, we can plug this R1 into the above equation and use it to solve for R2. Solving that equation for R2 gives us 3.28%. So this is year 2 spot rate. So to recap what we've done so far, we found 1-year spot rate, which is 3.2%, and we found year 2 spot rate, which is 3.28%. Now, the final step is to take the price of bond C, which is a 3-year zero coupon bond, currently traded at $88.55. And based on this equation, we will find year 3 spot rate, or R3. So the good news is that this equation is fairly simple in the sense that this is a zero coupon bond. So there are no intermediate coupons that this bond pays in year 1 and year 2. We've covered a situation like this in question 1. So here, just for simplicity, we've given you a 0 coupon bond. So solving this equation for R3 becomes fairly easy. If we solve it, we get R3 that equals to 4.14%. So what we found so far is that we found the term structure of interest rates for the first 3 years, for year 1, 2, and 3. So year 1 interest rate equals to 3.2%, year 2 interest rate equals to 3.18%, and year 3 interest rate equals to 4.14%. Now, let's examine whether bond D is priced fairly given the current term structure of interest rates. That, of course, assumes that bonds A, B, and C are fairly priced. So recall that bond D is, again, so it has 3 years to maturity. It has 3% coupon rate. So therefore, it pays $3 coupon at the end of year 1, $3 coupon at the end of year 2, $3 coupon at the end of year 3, plus the face value of $100 that it also pays at the end of year 3. So therefore, we can write down the following equation. So we are taking the first coupon, discounting it to present at year 1 interest rate, spot rate, which is 3.2%. We take the second coupon, which is again $3, and we're discounting it to present at year 2 spot rate, which is 3.18%. And the last payment of 3 plus $100, we're discounting at year 3 spot interest rate of 4.14%. So if you compute this, it gives us the price of $96.93. But recall that the quoted price of this bond was $99.5. So therefore, bond D appears to be overpriced relative to its fair price. And therefore, this presents an arbitrage opportunity. So to take advantage of this arbitrage opportunity, what we should do are generally two things. So we either sell an overpriced bond, or we buy the underpriced bond, or any asset for that matter. In this case, since bond D was overpriced, to take advantage of this opportunity, we should be selling this bond at the quoted price, or at $99.5. Now that we know there is arbitrage opportunity in this market, I will teach you how to construct an arbitrage trading strategy that takes advantage of it. In particular, we will construct such a strategy that pays off $100 today and nothing in the future. I will teach you a very universal approach that you can apply to construct arbitrage opportunities in any situation. So we're going to assume that we're buying XA amount of bond A, XB amount of bond B, XC amount of bond C, and XD amount of bond D. We will allow for these amounts for XA, XB, XC, and XD to be negative. This would imply that we are taking a short position or we're selling the corresponding bonds. So we want to construct a strategy that gives us $100 today. We can write the following equation. Bond prices multiplied by our positions should add up to $100. Here, the key would be that bond prices would come with negative signs because we're buying these bonds. So for example, if we're buying 1 unit of bond A, we will have to pay right now $96.90. This is the price of bond A. So in this case, we'll have a cash outflow of $96.90. If we are buying 2 units of bond A, then our cash outflow will be the price multiplied by 2. So therefore, this gives us the left-hand side of this equation, which means that we're buying XA of bond A, XB of bond C, XC of bond C, and XD of bond D. And so this expression gives us our total cash outflow that we have to spend on buying these bonds. And so this has to equal to $100 because we want a positive cash outflow today. So we want to construct a strategy that gives us $100 today. So you can immediately see that for this to work, that some of these amounts, XA, XB, and XC, and XD, has to be negative so that the corresponding cash flow is positive. So it makes sense that we would have to take a negative position or short sell one of these bonds. You can see that it's likely going to be bond D, because we've just determined in the previous question that this bond is actually overpriced. So this is just the summary of this. Now, the key to arbitrage is that our positions should be such that the bond payoffs or our payoffs from our trading strategy are zero in all of the subsequent years. And that's the definition of arbitrage. So we're making a positive amount today. So in this particular case, we're going to make $100. And our positions are fully hedged. So our cash flows are exactly zero in all of the subsequent years. So here, because the maximum maturity of the bonds here is 3 years, so we have to make sure that in years 1, 2, and 3, we get $0 cash flows. Let's start with year 1. So recall that bond A is a zero coupon bond with 1 year maturity. So it pays $100 in year 1. So therefore, the cash inflow or the positive cash flow, because we bought this bond, so at the end of year 1, we get $100 times how many units of this bond we purchased, so times XA. Now, bond B is a 2.75% coupon bond, and it's a 2-year bond, so it pays us the first coupon at the end of year 1. So we get 2.75 times XB. And bond D, so bond C is a zero coupon bond, so it pays nothing, and it matures in year 3. And bond D, it's a 3% coupon bond, so it pays us the first coupon, $3, at the end of year 1. So hence we get the following expression, and this has to equal to $0 because, again, we have to ensure that our cash flow at the end of year 1 is exactly 0. So for year 2, now bond A pays nothing, so it pays 0 because it already matured. Now bond B matures actually at the end of year 2, so it pays the second coupon of $2.75, plus it pays the face value of $100. And bond C pays nothing because it's a zero coupon bond that matures at the end of year 3. And bond D pays our second coupon, it pays $3. So we have the following equation, 102.75 times XB plus 3 times XD, and that equals to $0. So finally, for year 3, we get, so at that point in time, bond A already matured, so it pays nothing. Bond B also matured, so it pays nothing. Bond C pays its face value, so $100. And again, recall that this is a 0% coupon bond. And bond D pays its last coupon, which is $3, plus its face value, $100. So in year 3, we get the following equation. So 100 multiplied by XC plus 103 multiplied by XD, and that equals to $0. So let's put this all together. So we have the following 4 equations. So the first equation, it's our cash flow in year 1. The second equation is our cash flow in year 1. So the first one is our cash flow in year 0. Now let's put this all together. We have the following system of 4 equations with 4 unknowns. These equations represent our cash flows in years 0, 1, 2, and 3. So the goal right now is to solve the system of equations for XA, XB, XC, and XD. So here it's fairly straightforward how to solve this. So we can see that, for example, the last 2 equations, so they have just 2 unknowns, so they tie XB and XD, this is equation 3, and XC and XD, this is equation 4. So what I'm going to do is that I'm going to solve the last 2 equations for XB as a function of XD and XC as the function of XD. Now let's look at the second equation. Second equation has XA, XB, and XD. So I'm going to plug in the third equation, or XB, into the second equation, and then solve it to express XA as a function of XD. So this is me first step plugging XB as the function of XD into this second equation. And then the next step, I'm solving XA for XD. So I'm solving the second equation. And so now the second, third, and fourth equation right now give us xa, xb, and xc as functions of xd. And so if we plug these expressions into the first equation, it will give us it will give us just equation with the one unknown. So we'll have only xd in that equation. So doing that and solving that equation will give us xd equal to negative 38.85. So what this means, it means that we are selling, or we are shorting 38.85 units of bond D. So here I implicitly assume that I can actually trade fractions of the bond. So I can buy any fraction. So in this case, I'm buying 0.85. So I'm buying 38 whole units and 85 of fraction of bond D. So now this does make economic sense, because we've identified in the first part of this question is that bond D was overvalued, it was overpriced. So it was priced at 99.5 while its fair price was $96. So therefore it does make sense that for us to take advantage of this opportunity, we have to actually sell this bond at this higher price and therefore get this higher value to us right now. And then we're going to be taking long positions in the other three bonds to make sure that we get $0 payoffs in the years 1, 2, and 3. So now, since we have XD, what we can do is that we are plugging this amount of XD that we found in the equations that tie XA with XD, XB with XD, and XC with XD, and we get the following amounts for XA, XB, and XC. So XA and XB equal to 1.13, which means that we are buying 1.13 units of bond A and 1.13 units of bond B, and we are buying 40.02 units of bond C. So we're taking long positions in these bonds. Now, this is our arbitrage strategy. So we are selling 38.85 units of bond D, and we're buying the corresponding units of bonds A, B, and C. Now, the final step that I want to do here is that I want to actually verify that this trading strategy actually works. So what I will do is that I will plug in these amounts of XA, XB, XC, and XD that we found into our equations to make sure that we get the cash flows that we are thinking that we're getting. So if I'm plugging these numbers into the first equation, I get $100. So which means that me buying the corresponding amounts of bonds A, B, and C and shorting the corresponding amounts of bond D gives us exactly $100. In year 1, this equation tells us that we get exactly 0 as we expect. In year 2, we also get 0. And in year 3, we also get 0. So our arbitrage strategy indeed works. It gives us $100 right now, and it gives us nothing in years 1, 2, and 3. Let me show you how we can automate solving this arbitrage question. The first step that I will do is I will write down the system of equations that we had in the following matrix form. So I'll have matrix A, this is a 4x4 matrix, then I will have a column vector of x's, this is our unknowns, our positions that we're taking in these corresponding bonds. And this would equal to the payoffs that we get in years 0, 1, 2, and 3. So you can see that this system of equation written this way in the matrix form actually gives us the system of equations that we had before. Now we have to solve this for A. So all we really have to do is that we have to invert matrix A and then multiply it by the payoffs vector, vector B in this case. And let me show you how to do this using Excel tools. You can of course do it in any other software that you are more accustomed to using. So here, what I've done below is that I have written down the system, these numbers into just Excel arrays. And what I will do, so this is my matrix A, and this is my matrix B. So the goal right now is to invert these highlighted cells and then multiply them by this vector b. So the first, I will use M inverse function that inverts this 4x4 matrix. To do this, first I have to pre-highlight the location where I want these numbers to be inputted by Excel. And then I'm writing the function, so M inverse, and then I'm selecting array where I inputted these numbers. And then this is the key here is to hit the following three keys at the same time. So I have to hit Shift and Control. So I'm holding Shift and Control right now, and then I'm hitting Enter. So this way, right now, Excel, what it's done, it inverted these metrics. And so right now, what I have here on the screen is that it's inverted matrix A. So now all I have to do is that I have to multiply this inverted matrix by vector B. So here again, I will pre-highlight because I'm multiplying 4x4 matrix by vector 4x1. So the resulting output would be 4x1 vector, and this would be our vector of access. So I will use the following function. So M mult. So this is a multiplication function that multiplies two arrays or two matrices. So I'll select the first one, comma, and I will select vector B. And now I will also, so I will hold Shift and Control, and then I will hit Enter. And so this is the answer. So I'm going to highlight it in yellow, and you will see that this is exactly the numbers that we've had before when we were solving this system of equations by hand. So again, we're taking long positions in bonds A, B, and C, and we are shorting, we're selling bond D. So this is how you solve the system of equations in Excel. So overall, what we've learned in this question is that we've learned how to tackle this type of arbitrage problems. So all we have to do is that we'll have to assume that we're taking long positions in the instruments that we have. So here we have 4, we had 10. We would assume that we are taking XA, XB, and so forth positions in all of the 10 instruments. And then the key is to construct the payoffs that we get $100 in year 0, and we get $0 payoffs in all of the subsequent years. And then all we have to do is that we have to solve the system of equations as we just done here. And this way we would know which positions and which bonds to take in order to construct a profitable trading strategy. In this question, I will teach you how to find the price of a bond from a given yield to maturity, or YTM. Let's consider the following bond. It has 5 years until maturity. Its face value of $100. The coupon rate is 4.5%, and this bond pays annual coupons. And the yield to maturity on this bond right now is 3.15%. So given this information, the goal is to find the price of this bond. Now, if we're given YTM on any given bond, to find its price, all we have to do is we have to take all of the cash flows that this bond produces and discount them to present using yield to maturity. And this is exactly what I will do in this question. So here I have the cash flows that we get from holding this bond. I draw a timeline this way. And so the first payment in year 1, or precisely at the end of year 1, we get is $4.50. This is the coupon rate multiplied by the face value of this bond. So 100 times 4.5%. This is $4.50. This is how much this bond pays to us at the end of year 1. At the end of year 2, we get exactly the same payments, so $4.50. At the end of year 3, third coupon, same exact dollar value. At the end of year 4, another $4.50. Now at the end of year 5, we get our last coupon, $4.50, plus we get the face value, $100, paid to us when this bond matures at the end of year 5. Now we're taking all of these cash flows from this bond and we're discounting them to present using YTM. In this equation, it is represented by letter Y. So the first payment we're discounting to present by 1 plus y. The second one, because it occurs at the end of year 2, it's 1 plus y squared, 1 plus y raised to the power 3, and so forth. The very last payments, 1 plus y raised to the power 5. So the only thing we have to do here is that we have to plug in this YTM, or this y, which is 3.15%, into this equation and find each of these individual ratios, add them up, and this will give us the price of this bond. Now what I have done here is I've plugged in this y into this equation and computed the bond price. So the bond price is $106.16. So this is how we find the bond price from given yield to maturity. In the next question, what I will teach you is I will give you the bond with a given bond price, and I will ask you to do the converse calculation. So from given price, we will learn how to compute yield to maturity on a given bond. Now, let's discuss very important regularity here. So notice the relationship between the face value of this bond, which is 100, and its price, which is 106. The price is higher than the face value. In this question, this happens because the coupon rate on this bond, 4.5%, is higher than the yield to maturity, which is 3.15%. In this case, we are saying that this bond is priced at a premium because coupon rate is higher than the yield to maturity. If the yield to maturity was the same as the coupon rate, so let's say that yield to maturity in this question is 4.5%, we will find that the price of this bond equals to $100, in which case we say that this bond is priced at par. Now, conversely, if yield to maturity here was higher than the coupon rate of 4.5%, what we would have found in this question is that the bond price would be less than the face value of this bond. So it would be less than $100, in which case we say that this bond would have been priced at a discount. This happens again when the coupon rate is lower than the yield to maturity on this bond. In this question, I will teach you how to find yield to maturity. Consider the following 3-year bond. It pays annual coupon, it has face value of $100 and the coupon rate of 5.25%. The current spot interest rates are as follows. The 1-year rate is 1.1%, the 2-year rate is 1.15%, and the 3-year rate is 1.50%. We will compute yield to maturity on this bond. The first step in solving this question is to find the price of the bond. Now, we know how to find the price of the bond, so we're just taking the term structure of interest rates that we're given, and we're discounting each of the payments that we're getting from the bond to present using the term structure of interest rates. So first we are taking the first coupon, so it's $5.25. So recall that this bond pays 5.25% coupon. And so at the end of year 1, we get $5.25. At the end of year 2, we get another $5.25. At the end of year 3, we get the last coupon, again $5.25. And at the same time, we get the face value payment from the bond. That's another $100. And so we're discounting each of these payments using the corresponding spot rates to present. And this gives us the price of the bond of $110.98. Now, the second step is to write down the following equation. So this is the definition of yield to maturity. Yield to maturity is the interest rate that, if we're using it to discount all of the cash flows that we get from the bond, we get the current price of the bond. So therefore, we can write down the following equation. So 110.98, this is the current price of this bond, equals to the first coupon discounted to present at YTM, the second coupon discounted to present at YTM, plus the last coupon and the face value discounted to present at the YTM as well. So now
all we have to do is that we have to solve this equation for y. So this is just one equation with one unknown. The only problem here is that this equation looks nonlinear. So in particular, this is a cubic equation, so we have to use a lot of effort to actually solve this equation for y. So I'm going to show you how to do this in Excel. You can also use your calculators or any other software that solves nonlinear equations. I will show you two different functions that we can use to find yield to maturity in Excel. What I have done in the spreadsheet is I have entered basic information about our bond. So it has face value of $100, the coupon rate of 5.25%, and these are the spot interest rates, which we used to find the current price of the bond. So now here I will use a rate function. So if you start typing rate, you will see that this function requires a certain number of inputs. And these are the inputs that I've put here on top. So the first input would be the number of periods, which in the bond speak it is time to maturity of the bond. So it has 3 years to maturity, and so therefore it makes 3 payments. So this would be our first input. The second input would be the periodic payment that our bond makes. So in our case, this is annual coupon rate, which is $5.25. So this is the second input into this rate function. The third input is the present value, or the current price of the bond. Note that it is important to enter the price of the bond with a negative sign. So here I have negative 110.98. So this is my second input. This is my third input. So the price of the bond, again, it is negative. And the last input is the face value. So this is our terminal payment that we get from this instrument at the end of year 3. So you could see how this function is structured. So it has the current present value, which is negative. It has a terminal payment, which is the future or face value, which is positive. It has periodic payments. This is the second argument in this function, which is positive. And then the first one is the number of periods. So if we close this and we hit enter, this gives us yield to maturity on this bond, which is 1.48%. Now, the second way of solving this equation is to use internal rate of return function. So here, what I've done is that I'm showing the cash flows that we get from this bond. So again, in year 0, we have negative 110.98. So this is the price of the bond. So if we are a buyer of this bond, so this is our negative cash outflow in year 0. And then we have positive 525, positive 525, and positive 105.25. So another way of computing yield to maturity is just simply to use internal rate of return function, IRR, and then just entering the array of our cash flows and simply hitting enter. This will give us the identical answer. So the yield to maturity on this bond is 1.48%. Now, we do not know what internal rate of return is yet. We will learn this concept later in the course. But the yield to maturity on the bond is in fact the internal rate of return if you think of this bond as your investment. So therefore, we can use both rate function and internal rate of return. You could see that the internal rate of return function is actually much easier to use because all you have to do is that you have to enter the array of cash flows that you get from this bond. But we can use either of the two functions to find the yield to maturity in Excel. In this question, we will learn how to compute duration for different types of bonds. Assume that the yield curve is flat at 2%. Compute the Macaulay duration and modified duration for the following bonds. Bond A is a zero coupon, $100 face value bond maturing in 20 years. Bond B is a 5% coupon, $100 face value perpetual bond. We will assume that the coupons are paid annually. And C is a 5% coupon bond with a $100 face value maturing in 20 years. We will also assume that the coupons are paid annually. Let's start with question A and compute the duration for a zero coupon bond that matures in 20 years. Let's start with Macaulay duration. So by definition, Macaulay duration is given by the following expression. So it's 1 divided by the price of the bond multiplied by the sum, where we take each of cash flows that the bond pays in years t, and divided by 1 plus yield raised to the power t multiplied by the period in which this cash flow was paid, so year t. For zero coupon bond, all of the cash flows except for the very terminal cash flows are zero. So in this case, cash flows in year small t, where small t is strictly less than capital T, would be zero, and cash flow in year cap t is $100. So therefore, the Macaulay duration expression, the whole sum would be just consisting of one term. This is the terminal term. So we get 1 over p multiplied by $100 divided by 1 plus yield raised to the power capital T multiplied by capital T. So this is the terminal year in which the only payment that this bond pays actually occurs. So now notice that the price of the bond for a zero coupon bond is given by just simply $100 divided by 1 plus yield raised to the power capital T. And so what I will do right now is that I will plug in this price equation into the duration equation. And so you could see that that would just equal to 1 over p multiplied by p and multiplied by capital T. And so that would just give us capital T. So therefore, for a zero coupon bond, the Macaulay duration would always equal to the maturity of the bond. And this is a very important property for zero coupon bonds. So in this particular case, since our bond has 20 years to maturity, the Macaulay duration for this bond in part A of this question equals to 20 years. Now, the next step is to find the modified duration, which by definition is the Macaulay duration divided by 1 plus y, which is, again, yield to maturity on this bond. The modified duration of this bond then is given simply by taking 20, which is the Macaulay duration, divided by 1 plus 2%. And this gives us 19.61%. So to summarize, the Macaulay duration for this bond is 20, and the modified duration is 19.61. In part B, we're given a perpetual bond. So this bond pays 5% coupon and it has $100 face value. Coupons are paid annually. If you were to imagine the stream of cash flows that you get from this bond, it is a $5 paid annually and it's a perpetuity. So we'll start this question by deriving modified duration, and then we'll come back to Macaulay duration. You will see, because this would be the easiest to actually derive the modified duration first and then go back to Macaulay duration. So by definition, modified duration is negative 1 over p multiplied by the derivative of the bond price with respect to yield to maturity, y. The price of perpetual bond that pays coupon C annually is given by this. Because again, this is just a simple perpetuity with a discount rate of y that pays C, which is the annual coupon payment, every year. And as we've learned in lecture 3, the present value of this perpetuity is simply C divided by y. Now what we will do is we will first find the derivative of the price of the bond with respect to y. And this is very simply just negative c divided by y squared. Because again, the price of the bond was just c divided by y. And now we can plug this back into the modified duration equation. And this is going to give us minus 1 over p multiplied by minus c divided by y squared. And so you could see that c cancels out, y in the numerator and denominator, one of them cancels out. And so what is left is just 1 over y. So therefore, the modified duration for a perpetual bond is simply just 1 divided by y. In our case, yield to maturity is 2%, this bond, and so therefore the modified duration of this perpetual bond that is given in this question is just 50. Notice that it doesn't matter what coupon rate the perpetual bond actually pays. So the only thing that modified duration depends on is just yield to maturity of the bond. Now, the Macaulay duration we can compute based on the modified duration that we just computed. Remember that duration, or the Macaulay duration, is just modified duration multiplied by 1 plus y. And we know that the modified duration is 1 over y, so therefore the Macaulay duration is just 1 plus y divided by y. And so therefore, in our case, given that y is 2%, the Macaulay duration will be just 1 plus 2% divided by 2%, and that's going to be 51. So therefore, to summarize this question is that for this perpetual bond, given that yield to maturity in this bond is 2%, its Macaulay duration is 51, and its modified duration is 50. In part C, we asked to compute duration of a 5% coupon $100 face value bond that has 20 years to maturity. Let's start with Macaulay duration. Again, this is the definition of Macaulay duration written for this particular bond. So capital T here is 20. This is the number of years until the maturity of this bond. And since this bond pays annual coupon, the annual payment that we get from this bond is $5. So all we need to do here is that we need to compute the price of this bond and compute this sum, and this would give us the Macaulay duration. So we can compute this by hand, but it's a little bit tedious because we have 20 periods, and for each of the period we have to compute these numbers. So what I will do is that I will use Excel to illustrate how to compute the duration for this bond. In this Excel spreadsheet, I have put some basic information about this bond. So the current YDM is 2%, face value is $100, coupon rate is 5%. So this bond has 20 years to maturity, so therefore each year it pays $5 coupon up until year 20, when it pays the last final coupon of $5 plus the face value of 100. So the first step that I will do here is that I will compute the price of the bond. Because if you just look at the, again, definition of Macaulay duration, we need to know the price of the bond to compute the duration. So I will discount each of the individual coupons and cash flows to present, then I will add them up, and this will be the price of this bond. So I'll start with the very first coupon, so I'll take this $5, I will divide it by 1 plus yield to maturity on this bond, and I will raise it to power 1 in this case. This is when this cash flow occurs. And then I will do this for all of the 20 payments, and this is the present value of each of these individual payments that we get from this bond. So by definition, if I add this up, so this would be the price of our bond. So the price of this bond right now is $149.05. So first, notice that it does make sense. So if we compare the price of this bond relative to its face value, it's 149 versus 100. And it does make sense because, again, so this bond has a much higher coupon rate, which is 5% relative to its yield to maturity. So this bond should be priced at a premium, and its price should be above $100. So the fact that it's at 149.05 kind of passes the smell test in the sense that this bond is indeed priced at a premium. So now the next step, we need to compute the following sum. So I've written it down into the second equation where cash flow in year t divided by 1 plus yield raised to the power t is just the present value of that particular cash flow that occurs in year t. And then each of this present value of cash flow in year t, we have to multiply it by the year in which this payment occurs, and then we have to add them up. So this is how we're going to find the total value of this sum. So here is exactly what I will do. So I will take the present value that we just computed for the first payment, and I will multiply it by the year when this payment occurs. So in this case, it's year 1. So you could see that in year 2, I will be taking the present value of the second payment and I will multiplying by the year when it occurs. Again, this is year 2. And so I will do it for each of the payments. And now I will add them all up, and this would be the sum that we get in the duration expression. And now by definition, all we have to do is to compute the Macaulay duration, I have to take the sum that I just computed and divide it by the price of the bond. And this will by definition be the Macaulay duration. So this is how we can use the spreadsheet to find the duration of any bond. So if you have fewer than 20 years, for example, if you have 2 years, 3 years, you can do it by hand. In fact, you should practice to do it by hand because exam most likely is gonna feature a question where you have to compute the duration, but obviously we're not gonna ask you to compute the duration for a 20-year bond because this is too tedious. But it certainly you can do it for a 2-year or just a bond with a shorter maturity. Now, the final step here, what I will do is that I will compute the modified duration based on the Macaulay duration that you just computed, and modified duration would simply be just, again, the Macaulay duration divided by 1 plus the yield to maturity in this bond, which is 2%, and this is 14.15. So the modified duration for this particular bond is 14.15. Now, notice, going back to Macaulay duration, notice that this bond has 20 years to maturity, but its duration is 14.43. So remember that for a bond that pays 0% coupon, Macaulay duration equals exactly the maturity of the bond. But for any bond that pays non-zero or positive coupon, the Macaulay duration should be strictly less than the maturity of the bond. So in this case, the Macaulay duration is 14.43, which is less than 20, which again is reasonable because that number is less than 20. Let's summarize this question. For a zero coupon bond that matures in 20 years, Macaulay duration was 20, modified duration was 1961. For a perpetual bond, Macaulay duration was 51, modified duration was 50. And for a coupon bond, 5% coupon bond that matures in 20 years, Macaulay duration was 14.43 and modified duration was 14.15. Let's compare A and C. So one of the key things that we learned here is that for a zero coupon bond, the Macaulay duration equals the maturity of the bond. And so in that case, it was 20. Now, for the bond that also has 20-year maturity but pays a coupon, Macaulay duration has to be strictly less than 20. So if you compare A and C, again, C has Macaulay duration of 14.43, which is less than 20. Now, if we compare B and C, so both of these bonds pay the same coupon, but bond in C has 20 years to maturity, and bond in B is a perpetual bond. And so here, of course, you see that the longer the maturity of the bond, the higher is the Macaulay duration. So in this particular case, the Macaulay duration is 51, which is much higher than the Macaulay duration for a 5% coupon bond that matures just in 20 years. Generally speaking, if we're comparing two bonds, both of which have the same yield to maturity and the same coupon rate, the bond that matures later will have higher duration. In this question, we will learn about interest rate risk. Suppose that you manage a pension fund and your liabilities consist of the following three payments. 10 years from now, you have to make a payment of $40 million. In 15 years from now, you have to make another payment of $75 million. And in 20 years from now, you have to make a payment of $105 million. This is an approximation how actual pension funds work. Usually pension funds have to distribute pension payments to their retirees obviously more frequently than every 5 years. So this is just an approximation how a regular pension fund works. But you will see that the tools that we'll learn in this question can be extended to a more realistic scenario. We will assume that the term structure of interest rates is flat at 5%. Part A of the question asks us to use modified duration to determine what happens to the present value of liabilities of this pension fund when interest rates increase by 0.2%. And in part B of the question, we'll compute the actual change in the present value of liabilities of this pension fund, again, when interest rates increase by 0.2%. To compute the modified duration of the liabilities of this pension fund, let's first start by computing its Macaulay duration. By definition, the Macaulay duration is given by this expression. So this is the same expression as we've seen in the previous question. So let's first compute the present value of the liabilities of this pension fund. So that's our P. So in other words, let's compute the present value of all the future liabilities of this pension fund. So this is given by this expression. So we have to make our first payment of $40 million in the year 10. So the present value of that is 40 divided by 1 plus 5. 5 is our current yield to maturity. Raised to the power 10, because this payment occurs in the year 10, plus $75 million. This is our second payment that occurs in the year 15. And finally, $105 million. This is our last and third payment that occurs in the year 20. So we are discounting it to present again at 5% interest rate, and we're raising it to power 20 again because this cash flow occurs in the year 20. So this gives us the present value, or the value of the present value of the future liabilities of this pension fund, which is $100.21 million. Now, the Macaulay duration again is given by this equation. So we've computed P, the price. So now we can compute the remaining term. So this sum term, which here consists of just three terms because we have three liability payments. So 1 divided by 100.21, this is 1 divided by the price, or the present value of our liabilities, multiplied by 40 divided by 1 plus 5% raised to the power 10. So this is the present value of the first liability payment, multiplied by 10. So this is the year when this payment occurs, plus 75 divided by 1 plus 5% raised to the power 15. Again, this is the present value of the second payment, multiplied by 15. This is the year when it occurs, plus 105 divided by 5% raised to the power 20 times 20, because that payment occurs in the year 20. So when we compute this, the Macaulay duration of our liabilities is 15.75 years. Now, the modified duration, by definition, is just Macaulay duration divided by 1 plus yield. So in our case, this would be 15.75 divided by 1 plus 5%. And this will give us exactly 15. So the modified duration of our liabilities of this pension fund is just 15. Now, what we want to do right now is that we want to use this modified duration to approximate the change in value of our liabilities when yield curve shifts. So to be precise, technically speaking, when it's going to be a parallel shift in the yield curve. The change in the value of our liabilities can be approximated using the following equation. So the change in value, this is delta P, would equal to the original value of our liabilities times the modified durations times the change in the yield. And this goes with the negative sign because the value, the price of the bond, or the value of the bond, and yields change in the opposite direction. So if yields increase, the value of bonds will decrease. And so this is what will happen in our case. So now let's use the numbers that we have in this question. So the assumption is that the yield curve shifts up by 0.2%. So therefore, the value of our holdings will change by this much. So we are taking the original $121 million, we're multiplying it by the modified duration, which is 15, and we're multiplying it by the change in the yield, which is 0.2%. And this gives us negative $3 million. So as yield increases by 0.2%, the value of our liabilities drops by $3 million. And this answer is given to us by using this approximation, in which we're using the modified duration to compute the approximate change in the value of our liabilities. Let's compute the actual change in value of our liabilities. So the new yield curve right now is flat at 5.2%. So all we need to do here is that we need to take this new yield and compute the current present value of the liabilities of this pension fund. So this is the same expression as we had before when the yield curve was at 5%. So right now, the only difference here is that we're using the new yield of 5.2%. If we compute this present value of liabilities, we will find that the value is $97.25 million. So therefore, the actual decrease in value is what it was before, and before the value was 100.21 million, and the current value is 97.25. So the actual decrease in value is $2.96 million. This is by how much the present value of our liabilities dropped as a result of the increase in the yields, or again, the parallel shift in the yield curve. So let's summarize. When we use the modified duration and we found the approximate change in the value of our liabilities, the answer was that it decreased by $3 million. Now, when we compute the actual decrease was $2.96 million. So it's actually less than what was approximated by the modified duration. Now, the first thing to note here is that apparently modified duration actually worked really well to give us the approximate change in the value of our liabilities. So the only difference here is $0.04 million. But now, let's try to understand why the actual value decreases less than what duration approximation gives us. Let's look at this chart. And the answer will be that this is due to the convexity of the bond price as the function of the yield. So let's look at the right part of this picture. So this is where the yields increase. So if you look at, for example, just hypothetically speaking on this picture, so let's say that the yield changed from 5 to 7%. So based on this picture, so the blue line here is the duration approximation. By how much, if we're going to use modified duration, what would be the decrease in the value of our holdings as implied by the duration? And the red line is the actual price of the bond. And you can see that due to the convexity, that the actual decrease in the value of these liabilities would actually be lower than what it would have been if we just used the modified duration to approximate that change. And this is precisely what we found in this question. In this question, we will learn how to compute bond convexity, and we'll learn how to use it to approximate the change in the value of our holdings or in the value of the bond. So we'll assume that the yield curve is flat at 3.5%. We will assume that there is a $100 face value bond that pays annual coupons and has 5 years to maturity. The coupon rate is 5%. So first, we will compute the modified duration of this bond. Second, we will compute its convexity. Then we will use modified duration of this bond to try to find the approximate change in the value of the bond when interest rates drop or the yield curve drops by 1.5%. This is exactly what we've done in question 6. Then we will actually use convexity, the one that we compute in part B of this question, to find the approximate change in the value of the bond when interest rates drop by the same 1.5%. And then in the last part, we'll compute the actual change in the value of the bond. And then we'll compare that actual change to parts C and D of the question and see how well both parts C and D approximate the actual change in the value of this bond. Let's start by computing the modified duration of this bond. So this is very similar to what we've done in question 5. And the spreadsheet has the same template. The only difference is that this bond has 5 years to maturity. So the YTM on this bond, the current YTM is 3.5%. Its face value is $100. And this bond pays 5% annual coupon. So here we have the cash flows that we get from this bond. And the first step, what I will do is that I need to compute its price. So I will compute the present value of this cash flows. So we already done this calculation several times. And so if I compute present value for each of these 5 payments, I add them up. This will be the price of the bond. Again, I always recommend making sure that the price of the bond makes sense. So in this case, we expect this bond to be priced at a premium because the coupon rate on this bond is higher than its yield to maturity. And so the price of the bond 106 is above the face value of $100, so that this makes sense. So now the next step, I will compute the present value of each of these individual payments and multiply it by the year in which it occurs. I will add them up as well. And then I will compute the Macaulay duration by taking the sum and dividing by the price of the bond. And so this would be the Macaulay duration of this bond. So it's 4.56%. Again, recall the other check is that we expect the Macaulay duration here because this is a coupon paying bond. We expect the Macaulay duration to be lower than the maturity of the bond. So the maturity of this bond is 5 years. The Macaulay duration is 4.56. And finally, the modified duration is just the Macaulay duration divided by 1 plus the current yield. So the answer here would be that the modified duration is 4.41. In this question, we will learn how to compute bond convexity, and we'll learn how to use it to approximate the change in the value of our holdings or in the value of the bond. So we'll assume that the yield curve is flat at 3.5%. We will assume that there is a $100 face value bond that pays annual coupons and has 5 years to maturity. The coupon rate is 5%. So first, we will compute the modified duration of this bond. Second, we will compute its convexity. Then we will use modified duration of this bond to try to find the approximate change in the value of the bond when interest rates drop or the yield curve drops by 1.5%. This is exactly what we've done in question 6. Then we will actually use convexity, the one that we compute in part B of this question, to find the approximate change in the value of the bond when interest rates drop by the same 1.5%. And then in the last part, we'll compute the actual change in the value of the bond. And then we'll compare that actual change to parts C and D of the question and see how well both parts C and D approximate the actual change in the value of this bond. Let's start by computing the modified duration of this bond. So this is very similar to what we've done in question 5. And the spreadsheet has the same template. The only difference is that this bond has 5 years to maturity. So the YTM on this bond, the current YTM is 3.5%. Its face value is $100. And this bond pays 5% annual coupon. So here we have the cash flows that we get from this bond. And the first step, what I will do is that I need to compute its price. So I will compute the present value of this cash flows. So we already done this calculation several times. And so if I compute present value for each of these 5 payments, I add them up. This will be the price of the bond. Again, I always recommend making sure that the price of the bond makes sense. So in this case, we expect this bond to be priced at a premium because the coupon rate on this bond is higher than its yield to maturity. And so the price of the bond 106 is above the face value of $100, so that this makes sense. So now the next step, I will compute the present value of each of these individual payments and multiply it by the year in which it occurs. I will add them up as well. And then I will compute the Macaulay duration by taking the sum and dividing by the price of the bond. And so this would be the Macaulay duration of this bond. So it's 4.56%. Again, recall the other check is that we expect the Macaulay duration here because this is a coupon paying bond. We expect the Macaulay duration to be lower than the maturity of the bond. So the maturity of this bond is 5 years. The Macaulay duration is 4.56. And finally, the modified duration is just the Macaulay duration divided by 1 plus the current yield. So the answer here would be that the modified duration is 4.41. Let's compute convexity of this bond. I will start with definition. So convexity of the bond is given by 1/2 multiplied by the inverse price multiplied by the second derivative of the bond price with respect to YTM. So what I'm going to do right now, I will try to expand this formula by taking the second derivative of the bond price with respect to YTM. So let's write down the bond price as this. So this is just the present value of cash flows that we get from the bond discounted to present at its YTM. I will take the first derivative, which would be given by the following expression. Now I will take the second derivative, which would be given by this expression. I will write it down slightly differently by factoring out 1/1 plus YTM squared, so that under the summation sign we will get the following expression. And now I will plug in this derivative into the definition of the convexity. And so I'm going to get 1/2 multiplied by the inverse price multiplied by 1/1 plus yield squared multiplied by the following sum. Within this following sum, what I will do is that I will write down the ratio of cash flow received at in year t divided by 1 plus YTM raised to the power t as the present value of this cash flow. So this is why I factored out 1 plus y squared so that I can actually write down this as the present value of this cash flow. And so therefore, under this summation sign, we're going to have the present value of cash flow in year t multiplied by year t multiplied by year t plus 1. And so this is the expression that we can use right now to compute the convexity of the bond that we have in this question. This is a similar spreadsheet that we had in part A of this question. So here we're given our current YTM, the face value of the bond, the coupon, the cash flows that we get from the bond, and we already found the price of this bond, which was 106.77. So right now, let's use this expression that we just derived to compute the convexity of this bond. So first, for each year 1 through 5, I will compute this expression that we have under the summation sign. So this is the present value of each of these cash flows multiplied by t and multiplied by t plus 1. So for year 1, I will take the present value that we computed here. I'll multiply it by year 1 in this case and multiply it by 1 plus another 1. And I will do this calculation for each of these payments. And then I will add it up. And so you could see that to compute the convexity, I need to take 1/2, I need to divide it by the price of the bond, and I need to divide it by 1 plus y squared. And so first I will take the sum of these terms, and then I will divide it by 2. I'll multiply it by the price, and then I'll multiply it by 1 plus ytm squared. And so this would exactly be the convexity of this bond. So the convexity will be 12.38. Now, suppose that the interest rates drop by 1.5% at all maturities. This means that the yield curve shifted downwards by 1.5%. So first we will use the modified duration to determine first order approximate change in this bond price. So this is exactly what we've done in the previous question. So the change in the price of the bond is going to be negative, again negative sign because yields and prices go in the opposite directions. So it's going to be negative original price of the bond multiplied by the modified duration multiplied by the change in the yield. So recall that the price of this bond is 106.77. The modified duration that we computed in part A of this question is 4.41. And we're multiplying it by negative 1.5%. So this is the drop in the yield curve. So doing this calculation gives us delta P equal to $7.06. So therefore, as interest rates dropped by 1.5%, the bond price increased approximately by $7.06. Now, in this question, we will use both modified duration and convexity that we computed in part B to determine a second order approximate change in the bond price. The second order approximate change in the bond price is given by the following expression. So it's the original price multiplied by negative modified duration multiplied by the change in YTM plus the convexity of the bond multiplied by the change in YTM squared. So let's plug in the numbers that we have for the price, for the modified duration, and for the convexity of this bond. So the price is 106.77. The modified duration is 441. The YTM again drops by 1.5%. The convexity that we computed in part B of this question is 12.38 multiplied by 1.5% squared. Computing this gives us the change in price of $7.36. So as YTM drops by 1.5%, the price of this bond increases by approximately $7.36. Finally, let us compute the actual change in the price of the bond. And then we'll compare this change with approximations that we obtained in part C and D of this question. So the new yield to maturity on this bond right now is 2%. So it was 3.5, dropped by 1.5. So the new YTM is 2%. So given this new YTM, we can compute the bond price, which will be $114.14. So therefore, the actual change in the price of this bond is 114.14 minus the original price of the bond, which is 106.77. This would give us $7.37. Now, let's put this all together. So the change in value that we obtained using first order approximation or approximation only using modified duration was $7.06. The second order approximation that we obtained using both modified duration and convexity of this bond is 7.36 cents, and the actual change in the price of this bond is 7.37. Now you can see how remarkably close the second order approximation is to the actual change in the price of the bond. This is because the price of the bond as the function of yield to maturity is a convex function. And in this question, we've given you a very large change in the yield to maturity. So the original was 3.5% and it dropped by 1.5%. Recall that the first order approximation, or the approximation using just modified duration, would work well, but only for small changes in yields. But for these large changes, such as drop by 1.5%, the first order approximation doesn't work that well. It still works okay, but doesn't work as well as both modified duration and the convexity of the bond, where we can come as close as just 1 cent within the actual change in the value of this bond.